Greetings and welcome to Mom. This video is a video from our study of torsion, and the video is on the angle of twist. Angle of twist is if we were to have a shaft, and let's just let that shaft at this point be a solid circular shaft. And if we were to take a look at that shaft and what a line would look like if you had no torsion on the shaft. So that line would be right along the top of the specimen. And now you twist it. And now that line has moved, has deformed. The amount that it has deformed we call the angle of twist. So what are the different factors that determine how much the how much deformation there is? Well, the first factor is the torque. So if we've got an internal torque of some amount, then the more torque, the more angle of twist. In which case it belongs in the numerator. Now, this equation we're making is for lengths of a shaft where the torque is constant. And we've seen examples early in the homework where the external torques cause there to be different internal torques. And when that happens, you have to add up the angle of twist for each section where there's a different torque. Another variable, and so before I give us this next variable, I got to talk about what angle of twist means along the length of the beam. It's between any 2 points. So the angle of twist may be from here to here, or from here to here. And it turns out that the dependent variable in that dimension is the length. So we use the word length. And with the same torque and the same everything else, I'm going to have more angle of twist between two further away points than I will between two closer points. And so again, length ends up in the numerator. Well, I bet that if I asked the question, you could come up with some other determining factors, and one of those determining factors would be the shape of the cross section. And that would be correct. And as we've learned earlier, cross-sectional shape for circular members, we use, rather than area moment of inertia I, we use polar moment of inertia J. And if we went a little further, I bet you'd be able to tell me, well, doesn't the amount that it twists depend on what kind of material it is, whether it's rubber or aluminum or copper? And of course you'd be right. The variable, or it's not really a variable, I guess in this case, constant, the part of the equation that takes into account of that is the letter G. Now this might be new to us, but its concept isn't. G is the modulus of elasticity. Notice I left a blank there. Oh, wait a minute. No, you'd say, no, the modulus of elasticity is E. Not when we are in shear. E was the modulus of elasticity for axial loading. G is the modulus of elasticity for shear loading. Axial is perpendicular to the cross section. Shear is parallel to the cross section. And that's it. Now, if you had a couple of different sections along a length where any of these things changed, where the torque changed, perhaps the material changes, or the cross-section changes. If any of those things change, you just get the angle of twist for the smaller section and add them all up. Another possibility would be that the torque, for example, or the polar moment of inertia could be functions of continuously changing variables across the length. In other words, they could be a function of x get rid of that. Torque could be a function of x. J could be a function of x. G would not. That'd be for the material. And if these are continually changing, then what we're going to do is just integrate with respect to x. So in place of the L is the dx, add up all the dx's for all the differing torques and moments of inertia, and we would integrate from 0 to L. So discrete, continuous, and there we have angle of twist. There is a sign convention. And if you have a beam, a shaft, what you do is you look at any particular spot. Let's take a look at that spot, got a little free body diagram. And if the internal torque there is such that when you wrap your right hand around in the direction of the torque and your thumb points outward, we call the torque positive and the angle of twist positive. Whereas if the internal torque were pointing, in other words your thumb, were pointing into the shaft, at that point the torque would be negative and the angle of twist would be negative. This allows us to look and see what is the angle of twist doing. Is it always adding as you go through different sections, or sometimes adding, sometimes subtracting? All right, well, that's really it for angle of twist. Well, no, let's do one more thing as long as we're here. Let's take a look at what the units will be. Let's take a look at the units using the world-famous checkmark method. Let's use some English units. And torque will be in foot-pounds. Length will be in feet. Polar moment of inertia would be in inches to the fourth or feet to the fourth. So T, L, J, and G. And you can find G. Another name, by the way, another name for the shear modulus of elasticity is the modulus of rigidity. And you can find that in the back inside cover, just like we did for E. And it has units of PSI, pounds per inch squared. Let's keep everything constant here, pounds per foot squared. So I did this in so that we have all the same units, though we would maybe see different units. Instead of pounds, maybe kips; instead of feet, maybe inches. But our dimensions are all the same. So what happens here? Foot, foot, that's foot squared. Foot squared and foot squared is foot to the fourth, pound and pound. It's like our angle of twist doesn't have any units. It's like it's unitless, but it's not. It is radians, and as we remember, radians are dimensionless. So when you find angle of twist, you will be getting an answer in radians. All right, that's it. Have a nice day.